Assalamualaikum and welcome to our presentation for SFE3043 Sensor Technology 2. Today, we will discuss optical sensors in aerospace application, specifically looking at structural health monitoring for aircraft wings and parts. My name is Mohammad Hakimi bin Shahrul Norrizan and my partner is Mohammad Mukhlis bin Romzi. In this presentation, we will explore how modern aircraft transition to advanced composite materials like carbon fiber reinforced polymers or CFRP, which improve fuel economy but are vulnerable to hidden internal damage. We will explain how we use fiber bright grating or FBG sensors to detect this damage in real time to ensure early safety and operational efficiency. We will also address the main technical challenges, implementation problems, and future solutions for this technology.
In aerospace engineering, the material landscape is changing rapidly. For decades, aluminium and titanium were the industry standards. However, we are aggressively moving away from these traditional metals due to the heavy weight and long-term susceptibility to corrosion. The modern standard relies on advanced composite materials such as carbon fiber reinforced polymers or CFRP. Today, these standard materials make up approximately 50% of the primary structures in commercial aircraft. These polymers are significantly lighter than traditional metals. By drastically lowering the overall weight of the aircraft, these composites offer airlines a better fuel economy than traditional designs. But this strength introduces a unique vulnerability. Unlike metals, which dent visually, composites are susceptible to an invisible threat. Environmental factors like lightning strikes or sharp impacts can cause internal matrix cracking or delamination, that is, damages hidden deep inside the structure that cannot be seen with the naked eye. To catch these hidden threats, we integrate an optical concept into mechanical engineering. The most established tool for this is the fiber bright grating or FBG sensor. The FBG sensor uses light reflection where it separates and detects specific wavelengths, just also known as the bright wavelength. And when aircraft wings bend under aerodynamic strain or when it experiences localized temperature shift, we can detect a shift in its bright wavelengths. And then onboard computer system instantly measure this exact shift in the reflected light's wavelength. This real-time data is translated directly into precise measurements of the structure's physical integrity. This capability transforms aerospace operations in three major ways. First is real-time safety, where it provides continuous monitoring of the aircraft while it is actively in flight. Next, the extreme sensitivity of the FBG sensors allows pilot and maintenance crews to catch small and subtle structural changes. This allows early intervention to be made before they can develop into catastrophic mechanical failures. And with early problem intervention, we can significantly reduce maintenance costs and enable a more efficient operation of the aircraft.
Today we will discuss the major challenges when we use sensors in aerospace engineering. First, let's look at the technical limitations. Common sensors like fiber bright grating, or we call it as FBG, and piezoelectric types are very fragile. They break easily under the high heat and pressure used to build aircraft parts. Second, putting sensors inside composite materials makes the structure weaker. Large sensors create extra pockets of glue that causes tiny cracks. Third, some sensors are too sensitive, so they measure the wrong type of pressure and give incorrect safety information. And finally, composites hide damage deep inside their layers. Because their strength changes in different directions, it is very hard to predict exactly how they will feel. Beyond these technical issues, specialized sensors cost a lot, and all dye penetrant tests use hazardous chemical. Crucially, when a sensor fails to detect hidden damage, that spot can grow quickly and cause sudden dangerous structural failure. Furthermore, real-time monitoring generates massive amount of data, which causes storage issues. Sensors must also survive 30 years of extreme heat and flight vibrations. Finally, other airplane systems cause electronic noise, so it is hard to meet strict rules from the Federal Aviation Administration (FAA) and standards like Aeronautical Radio Incorporated (ARINC 429) when engineers scale these systems up for full-size aircraft.
Now that we understand the vulnerabilities of composites and the fundamentals of optical sensing, let us look forward. How do we optimize, scale, and protect these systems? Our first priority is survivability. The manufacturing process of an aircraft or component is incredibly harsh. To prevent fragile optical sensors from breaking, engineers can apply robust, specialized protective coatings made of materials such as polyamide, Teflon, or acrylite, ensuring the sensor survives under extreme conditions. At the same time, we are pushing the limits of miniaturization by developing small diameter optical fibers that are 40 to 80 micrometers thick, which drastically reduce the physical footprint of the sensor. This ensures maximum timekeeping and strain sensitivity, while also minimizing structural degradation to the aircraft part itself. With the rise of artificial intelligence, integrating AI into the architecture allows us to move beyond basic damage detection. Computers can now process sensor data to actively predict the durability of a wing or component before it even shows any sign of wear. And this AI integration can translate into massive operational savings. By utilizing neural networks to analyze microstrains and identify anomalies in real time, airlines can optimize their operational workflows and according to route and accrete, potentially reducing unplanned maintenance by up to 45% by the year 2030. Finally, we address the system efficiency and sustainability. Traditional structural monitoring requires miles of heavy copper wiring, adding dead weight to the airframe. Transitioning to a network of smart wireless sensor eliminates this physical burden, making the aircraft lighter and more fuel efficient. In fact, these wireless architectures are estimated to be up to 60% lighter than traditional wired setups. By removing a network of cables across a commercial fleet, this technology directly lowers fuel burn, reducing carbon emissions, and minimizing the aviation industry's environmental carbon footprint. Previously, we analyzed the highly technical work of advanced composites, fiber optic sensors, and predictive AI. Now, we ground this modern engineering suite within the profound network of the Islamic worldview. In the Islamic intellectual tradition, human reason, also known as Aqli, and divine revealed knowledge, like the Quran and the Hadith, also known as Naqli, are never viewed separately. Instead, they complement each other, working together as two halves of a singular whole, designed to study, understand, and respect the universe as part of Allah's limitless wisdom. This integration of knowledge elevates the identity of Muslims. In Islam, scientists, researchers, and engineers are not merely employees executing a technical task. They bear a sacred duty. They are trusted with an amanah, or a profound moral responsibility to act as Khalifa, or caliphs, and caretakers of the earth. To act as a Khalifa means managing Allah's creation with the utmost wisdom, safety, and ethical responsibility. When we deploy intelligent sensors to monitor structural fatigue, prevent catastrophic failures, and protect hundreds of human lives, we are directly fulfilling this sacred stewardship. Real-time safety engineering becomes an active expression of our faith.
إن إن في خلق السماوات والأرض واختلاف الليل والنهار لآيات لأولي الألباب.
To understand how this sacred responsibility directs our intellect, we look at the Holy Quran itself. In Surah Ali Imran, verse 190, Allah states, "Indeed, in the creation of the heavens and the earth, and the alternation of the day and night, there are signs for people of reason." The Quran explicitly mentions Ulul Albab, which means the people of reason and intellect. This verse actively commands us to reflect deeply on the wonders of creation. Ultimately, this pursuit of aerospace knowledge represents the highest form of ilmun naf'i, that is the knowledge that brings about benefit to humanity. By protecting travelers, advancing safe global connectivity, and preserving human life through smart sensing technology, we are carrying out our duties as Khalifah on this earth. It is proof that when human reason is guided with revelation, engineering and physics become a profound fulfillment of our purpose as humans.
To conclude, our research shows that these sensor systems successfully detect invisible internal damage like matrix cracking. This capability is critical because it keeps composite structures safe. To achieve this, engineers use highly sensitive tools to monitor strain and temperature continuously. Finally, these modern methods successfully overcome major technical problems such as sensor damage during manufacturing, massive real-time data streams, and environmental noise. Next, let us look at the future. Aircraft maintenance will change because we will fix parts before they break. Computers will analyze sensor data to identify hidden issues early. Furthermore, new systems will use the ARINC 429 standard protocol so that different aircraft computers can share information without errors. Lastly, researchers continue to develop ultra-thin fiber to monitor the safety of large aerospace components at all times. These are some of the references we have collected during our work. Thank you so much for listening. Assalamualaikum warahmatullahi wabarakatuh.